Hey everyone! In this video, we're going to be talking about the rate of change. So if you remember, another way that we can use slope is to describe the average rate of change of a function on a given interval. Well, sometimes we want to find the instantaneous rate of change. In other words, what is the rate of change at a particular instant on our function? And that's what we're going to be taking a look at mainly. But let's start with just the way that we find average rate of change. So the average rate of change of a function, let's say we're looking at the average rate of change on an interval from c to x. Well, the way that we find this average rate of change is we're going to be finding the slope. So we'll do f of x minus f of c, and then we'll divide that by x minus c. Now, if I compare this to the instantaneous rate of change, well, now we don't want an interval. We want the rate of change at just one point. So we're going to bring the two ends of our interval, we're going to bring them closer and closer together, and we can do that with a limit. So the instantaneous rate of change is going to be equal to the limit as x approaches c of our slope function. So f of x minus f of c over x minus c. And again, another way that we can write this is using prime notation. So I could say f prime of c. And this is what we're going to use in our example. So let's take a look. So here I have a function f of x is equal to x squared minus 5x. And I want to find the instantaneous rate of change at the value of c is equal to 1. So let me just write down our formula again. So f prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. So just as a little side note, let's find f of c right away. So f of c, so that means f of 1. That's going to be equal to 1 squared minus 5 times 1. So 1 minus 5, we get negative 4. So that way we can plug that in. And let's plug in everything else we know as well. So we still have the limit out front. Now it's going to be the limit as x approaches 1, because c is equal to 1. F of x is our original function. So x squared minus 5x, and then we're going to subtract the value for f of c we just found. That was negative 4. And then this is going to be divided by x, and then the value for c is 1. And just to simplify a little bit here, if I'm subtracting a negative, that'll turn into plus 4. So here we end up with the limit that we want to evaluate. Now, the first thing to notice is if I want to evaluate this, I cannot just plug in 1. If I try to do that, I end up with an indeterminate form, meaning I end up with 0 divided by 0. So we can't evaluate the limit that way. So the first thing we have to do is try and simplify a little bit. So we have a polynomial in the numerator, and let's start by factoring that. So we need two numbers that multiply to 4 and add to negative 5. So that factors into x minus 1 and x minus 4. And this is still over x minus 1. And now in this factored form, we can see that we have something that will simplify. So the x minus 1 and the x minus 1 will cancel out. And then what we're left with, so f prime of 1 is going to be equal to the limit as x approaches 1 of just x minus 4. And now in this simplified form, we can substitute in 1. So we end up with 1 minus 4. So our instantaneous rate of change, f prime of 1, is equal to negative 3. In other words, that is the slope of the tangent line at that value for c. Now, let's say you didn't want to have to go through all of this work every single time you wanted to find the instantaneous rate of change. what if you wanted a formula that would allow you to do that for this specific function? Let's take a look at that next. So now we're going to be using the same function, but instead of finding the instantaneous rate of change at a specific number, let's keep it general, and we'll find the instantaneous rate of change for any real number c. So we're going to do the same process, but instead of using a value, a number, we're just going to keep it as a variable. So again, let's see, we want f prime of c, and this is equal to the limit as x approaches c of f of x minus f of c divided by x minus c. So just a little side note again, if I want to find f of c, remember we just substitute in c for x. So this is going to be equal to c squared minus 5 times c. So let's plug in everything we know. So we still have our limit, the limit as x approaches c. F of x is our original function. So we have x squared minus 5x. And then we're going to subtract f of c, which is c squared minus 5 times c. And then this will be divided by x minus c. Let's start by simplifying and distributing the negative. Our limit has to come down every step. And distributing the negative, we end up with x squared minus 5x minus c squared plus 5 times c. And notice again that if I want to evaluate this limit, I cannot just plug in c. I would end up with an indeterminate form on this one as well. So just like we did in the last example, when we were evaluating for a specific number, we need to try and simplify this. So the first thing I'm going to do is I'm actually going to rearrange the numerator a little bit. So I'm going to take these two squared terms, I'm going to group them together. So we have x squared minus c squared. And then I'm left with the minus 5x and plus 5c. Now the reason I wanted to do that is because I have x squared minus c squared. That's the difference of perfect squares. And I know that I can factor that. So let's move over here. F prime of c. Okay, we still have our limit. Factoring that difference of perfect squares, we end up with x plus c and x minus c. And then actually in those second two terms, minus 5x and plus 5c, I can factor out a minus 5. And that leaves me with an x minus c. So factoring those out, I can see now that I have a common factor in the numerator and the denominator that's going to simplify. So there's an x minus c in both of these terms in the numerator, and I have an x minus c in my denominator. So that will cancel out each of those. So what I'm left with is the limit as x approaches c, and we have x plus c minus 5. And now in this simplified form, we can substitute in c to find our limit. So plugging c in for x, we have c plus c, and then minus 5. And simplified, f prime of c is equal to 2 times c minus 5. And this gives me a general formula that I could use to find the instantaneous rate of change for any value of c. If we go back to the value of 1 that we had before, we found that our instantaneous rate of change at 1 was -3. Well, if I plug in f prime of 1, it's going to be 2 times 1 minus 5, so we also get -3.